Hello all. This is a paper I prepared somewhat in a rush. So I literally went over this this morning, and I'm recording this video in the afternoon. Okay, and this is because I had a viewer requesting that I go over the 2022. So this is the 2022 paper. So he or she, I don't know, requested that I should go over the 2022 Advanced Physics 2, paper 2 from Edexcel. So this is not the international A levels, these are the regular. Can you call them regular? I don't know. I mean, the UK probably is better. So these are the UK exams, okay? I try to avoid doing this because if eventually, if the channel keeps growing, at some point everybody will be requesting something else, and it's just me, guys. I mean, I don't know, but maybe in the future I will have I don't know. This will be monetized, and I can hire people to do this. I don't know. We'll see. But anyway, this is a 2022 paper, and the reason why I'm recording this somewhat in a rush is because you guys are taking this test on Monday, okay? So, I mean, it's only gonna be useful if I upload now. So, I'm gonna go over this a little bit fast, okay? So, the general things I always say, you have 1 hour and 45 minutes, so 105 minutes to finish this paper, and it awards, I don't know, somewhere in the neighborhood of 90 marks. We can check really quick. Uh, yes, and it awards 90 marks. So anyway, the thing I always say is that you should spend about a minute per mark. So if a question awards 1 mark, it should take you about a minute. If it awards 15 marks, it should take you 15 minutes. And this is so you time yourselves. Okay, I'm saying this so you time yourselves, so you don't run out of time and you score maximum points. In the multiple choice section, sometimes you can arrive at the correct answer just by eliminating the wrong answers. Okay, so that's the other exam technique I always mention. Um, the other thing is a general thing. If you don't know how to start working on a problem, immediately skip it and start working on something that you actually know, and then build momentum and confidence and come back to the problem later. You might have a better idea about how to proceed on a problem. Read the formulas that they give you. Sometimes it gives inspiration about what you need to do. And in questions that do not involve calculations, okay, those questions, if they award 6 marks, that means that you should provide about 6 sentences justifying or disproving whatever it is they are asking you to do. Okay, I think I said it all. Let's start. Question 1. A skydiver steps out of an aeroplane and falls from rest towards the ground. Her parachute opens a short time after she reaches terminal velocity. Okay, so that's a key there. Which of the following statements is correct for the vertical acceleration A of the skydiver until her parachute opens? So let's remind ourselves that if we have an object in free fall, the forces are the weight and the drag force, which is proportional to the velocity. So as the velocity increases, the drag force increases, and there is a small upthrust, but this is air, guys. I mean, the upthrust is negligible, otherwise we will be flying, right? But anyway, it's there anyway. So the sum of all forces in this case, if we take as positive, the downward direction is weight minus drag minus upthrust, okay? And this is equal to ma, okay? Terminal velocity means that a is 0, or otherwise the weight becomes equal to the drag plus the upthrust. So the correct answer is a, okay? I'm not going to argue over the other options, so let's move on. I mean, I'm not going to argue why they are wrong, so let's move on. Light traveling in glass of refractive index Ng is incident at the boundary with water of refractive index Nw. The critical angle for the boundary is C. Which of the following expressions is correct for this boundary? So we pretty much have to find the critical angle. So if this is the glass and this is the water and this is the ray incident on the interface there, we will have n glass times the sine of the critical angle is going to be equal to the index of refraction of water times the sine of 90 degrees, which is 1. Okay, so sine of the critical angle is going to be n of water over n of glass, or option B. Okay, let's move on. 3. Sound waves can diffract around obstacles as shown in the diagram. And you see that the wavelength, okay, is about the same as the obstacle. So the diffraction effect is greater, this is option A, is greater for large amplitude sound waves. No, the amplitude doesn't affect diffraction at all. B, greater for low frequency sound waves. Okay, let's think about that. The velocity of the wave is lambda times f, right? So lambda is equal to the velocity over the frequency. So if frequency decreases, lambda increases, okay? So this works actually because with a larger than the obstacle wavelength or about the same, we get greater diffraction. So B is a candidate. Let's read C. Independent of the frequency of the sound waves, that's not true because the frequency affects the wavelength. D, independent of the speed of the sound waves, that's not possible because the velocity is proportional to the wavelength. So B is the correct answer. Okay, so the diffraction effect is in general greater for longer wavelengths. Okay, for a fixed obstacle like this one. So when I say longer, I mean something like this. Okay, so it's a little bit longer than the original wavelength. Okay, so B is the correct answer. 4. Which of the following is a valid unit for luminosity? Okay, so luminosity is actually given in watts. Okay, I'm trying to think of a good rule to help you remember this. Okay, luminosity goes back to the Boltzmann, excuse me, law, but that's difficult to remember. So, luminosity is measured in watts in general. Maybe intensity. Usually you remember that intensity is watts per meter squared, but intensity is luminosity over some area. Okay. But anyway, the units for luminosity are watts, and watts are joules per second, which is option C. Okay, let's move on. 5. Betelgeuse is a red giant star. Okay, the surface temperature of Betelgeuse is Tb, and the surface area of Betelgeuse is AB. The surface temperature of the Sun is Ts, and the surface area of the Sun is As. Which row in the table shows a correct comparison of the surface temperature and surface area of Betelgeuse with those of the Sun? Okay, so the surface temperature is going to be less than that of the Sun, and the reason is because this is a red giant star. So in the Hertzsprung-Russell diagram, if you remember, main sequence stars are here in the diagonal, and temperature increases to the left, and red giant stars are up there. Okay, so their surface temperature is low. Okay, so the surface temperature of Betelgeuse is less than that of the Sun, and of course this is a giant star, so it's much larger. Its surface area is larger than that of the Sun, so the correct option is B. Okay, because they tell us T of Betelgeuse larger than T of the Sun, that's false. And then A, the surface area of Betelgeuse is larger than that of the Sun, which is true, so B is the correct answer. So let's move on to the next question. 6. In a particular radioactive decay, there is a mass decrease equivalent of 0.05 atomic mass units. Which of the following expressions gives the energy released in MeVs? Okay, so the energy released is equal to delta M times C squared and we will have to somehow make this work with MEVs. So delta M is 0.05 atomic mass units, and one atomic mass unit is 1.66 times 10 to the negative 27 kilograms. And then we have to multiply this. Okay, I'm gonna use a clean page, and I'm gonna try to cut this. Okay, cut, and move here, and paste. Great. Okay, so that's the mass of one atomic mass unit. Okay, it's really close to the mass of the proton, but the proton is 1.67 times 10 to the negative 27 kilograms. Okay, and then times c squared, oops, times c squared. And then to convert this, so this is the result. So we have kilograms meter squared over second squared, okay? And this is known as 1 joule. So to convert to EVs, we have to divide by 1.6 times 10 to the negative 19, and this is joules per electron volt. So this joules is cancelled. And additionally, we have to multiply by 10 to the 6 to make these MEVs, okay? And we multiply the denominator, because if we multiply the denominator, we will have MEVs up top, okay? So this is option, so we can combine this into 1.6 times 10 to the negative 13. And if we go to the back of the paper, we see that the correct answer is C. D is almost correct, but notice that that's the mass of the proton, okay? So in case you don't remember this, I mean, I remember the weight of one atomic mass unit because I'm a nerd and a nuclear physicist, but if you don't, it's this is actually given. If you go back to the back of the paper, where is it? Over here, okay? So yeah, don't risk it if you don't remember it, okay? I mean, it's cool to remember it because you're gonna save yourself a few seconds searching the constant, but in case you don't remember it, look it up, okay? Okay, this was question 6. Wait, okay, sorry, I skipped one question. So question 7 now. Air is trapped in a glass tube. When the air is forced into a smaller volume at a constant temperature, the pressure increases. Which of the following statements about air molecules is a reason why the pressure the trapped air exerts on the tube increases? So you have a tube, maybe there is a piston, so there is some air, and then with the same piston we reduce the space, okay? So the same gas molecules at the same temperature occupy a smaller space. Okay, A, the molecules have a greater mean kinetic energy. That's totally wrong, okay, because the kinetic energy is 3/2 kT times the number of molecules. The temperature is the same, so the average kinetic energy is actually the same. Okay, B, the molecules make more frequent collisions with each other. That would not affect the pressure at all, okay? So let's move on to C. The molecules make more frequent collisions with the walls of the tube. That's promising. It's actually the correct answer. So, but anyway, let's read D. The molecules experience a greater change in momentum when they collide with the tube. Tempting, but no. C is the correct answer because you have more collisions, which increase the pressure. Okay. Let's move on to question number 8. Okay, question 8. Total internal reflection occurs when light is incident on the boundary between medium 1 and medium 2 as shown. The refractive index of medium 1 is N1 and the refractive index of medium 2 is N2. The critical angle for the boundary is C. Which row of the table is correct? So this phenomenon can only be observed, excuse me, if N2 is less than N1. Okay, and then theta must be larger than or equal to the critical angle. So this is option D, right? Yes. Okay, Question 9. The focal length and power of a converging lens, converging glass lens, okay, are determined for the lens in air. The lens is then immersed in water. Which row in the table shows how the focal length and power of the lens change? Okay, so maybe it's good to have this in your notes. I'm gonna write it down. So this question 9. So the refractive index contrast. So the refractive index contrast is lower, okay, because n water is larger than n of air, which is 1, right? So the lens bends less light, so the focal length increases. So it doesn't focus the light as easily as in air, pretty much, okay? So F increases, but if F increases, power, which is 1 over F, decreases, okay? So let's go see what the correct answer is. So the focal length increases and the power of the lens decreases, so option C is the correct answer, okay? Now, question 10. A student used a Geiger-Müller tube to determine a value for the background count. He recorded the count for 2 minutes every 15 minutes. So every 15 minutes, he recorded the count for 2 minutes, okay? So he started now, he waited 2 minutes, and then after the 2 minutes are gone, have passed, excuse me, he waits 15 minutes and then does the same for another 2 minutes. Then after he does that, he waits another 15 minutes and does the same measurement for 2 minutes. I hope this is clear. Okay. The counts are not the same. Okay. Which of the following is the reason for this? Okay, I mean, they are not really different. I mean, I would worry if I saw something like 34 and then 2 and then 68. Okay, so that would flag a problem in the measurements or with the equipment or something. But they are close together. So the correct answer is actually A. The background count rate is random. Okay, so this is to be expected. B says that the counter is incorrectly calibrated. I mean, as I just described, you will see crazy fluctuations in that case. C, the temperature has not stayed constant. I don't think so, and also it wouldn't affect the result. Then D, there is a systematic error in the measurement. Again, you will see crazy things going on, so no. And another thing about randomness, if he recorded for an hour and then waited 2 hours and then recorded for an hour again, then the counts will be really close together, okay? Because so you have the large numbers averaging into the same number pretty much, if that makes any sense. So it's a statistical thing. You probably learned that in statistics, okay? So let's move on. Question 11. The lens of a mobile phone camera has a focal length of 4.25 millimeters. Light is focused onto light sensors at the back of the camera as shown. The camera is initially focused on an object in the far distance. Calculate the displacement of the lens that would be required to focus on an object 25 centimeters from the camera. Okay, so 1 over u plus 1 over v is going to be 1 over f, where of course u is the distance of the object, so 1 over 0.25 plus 1 over the position of the image is going to be equal to 1 over 4.25 times 10 to the negative 3, which is the focal length converted to meters. And I also converted the object's distance in meters. Okay, so 1 over v is 231.29 meters to the minus 1. So v is 4.32 millimeters. Okay, so with f equal to 4.25 millimeters. Okay, the lens have to move. Oops. The lens have to move by 4.32 minus 4.25, which is 0.07 millimeters. Okay, away from the sensor. Okay, so maybe somewhere here. So they focus the object on the sensor. Okay, that's the idea. Okay, B, state why the lens and the light sensors in a mobile phone camera can be positioned, a fixed distance apart. So for typical object distances, okay, so which are much larger than f, okay, or u is much u is much larger than v, okay. So what I'm trying to say is that because u is large, 1 over u is approximately 0, so v, the position of the image, is approximately equal to f, okay. So v is approximately equal to f regardless of the object distance, okay. So the displacement needed is negligible. Okay, this was question 11. I hope it makes sense. Okay, question 12. In February 2021, the spacecraft Perseverance rover landed on Mars. When the spacecraft was 11 kilometers above the surface of Mars, parachutes opened to slow the descent. The parachutes detached from the spacecraft when it was 2.1 kilometers above the surface of Mars. Calculate the change in gravitational potential energy of the spacecraft during the parachute section of its descent. So, the change in gravitational potential energy is equal to the mass of the spacecraft times delta V, okay? And delta V is going to be, okay, m of the spacecraft times minus gm, this is the initial gravitational potential energy, r plus h2, where h2 is 11 kilometers above Mars, and then we have to subtract something negative, so we have to add, so minus of minus makes a plus, gm over r plus h1, where h1 is 2.1 kilometers, okay. So let's take out the gm times the mass of the spacecraft. We don't need to divide by anything, I'm sorry. And then we have 1 over minus 1 over r plus h2 plus 1 over r plus h1. Okay, and now we have to plug in numbers. So we have 6.67 times 10 to the negative 11. And I'm going to plug in the numbers, the units. I don't have enough space. So I'm going to put the units here. So the units for G are newtons meter squared over kilograms squared. Then we need the mass of Mars, which is 6.39 times 10 to the 23, and then kilograms. Whenever I work out problems, I put all the numbers to the left and all the units to the right. Okay, in this case, I split over 2 lines because there's not enough space. Okay, then the mass of the spacecraft is 1,300, and then kilograms, so kilograms squared. So this cancels. And now we have to multiply by 1 over 3,390,000 meters, okay, which is the radius of Mars, plus h1, which is 11,000, okay, and this comes with a minus, I forgot the minus, plus 1 over the same thing, 3,390,000 plus 2,100, okay, and we need meters in the denominator, so meters cancel. Okay, and I'm gonna use a clean page. So this works out to be 3.39 times 10 to the 7 joules, which is about 3.4 times 10 to the 7 joules. In the mark scheme, they probably have this as minus 3.4 times 10 to the 7 joules. This denotes a decrease in the kinetic, in the gravitational potential energy, because something that is higher up in the gravitational field has more potential energy than something that is lower, right? But anyway, this is the answer. If they have a minus sign, please include it, but it's optional. I mean, the positive answer works as well. So let's move on to the next question. This was, even though I studied nuclear physics for my PhD, I never saw a question like this. And I'm not sure that the half-life of actinium-225 is actually 10 days, because it looks too round. I mean, too good to be true. So, but anyway, the question asks, actinium-225 and bismuth-210 are radioactive isotopes. A sample of each isotope is prepared so that each sample has the same number of nuclei initially. Explain why the activity of each sample will be the same after 10 days. So, we have actinium-225, okay, with a half-life of 10 days, okay, and therefore lambda of, let's call it 225, is going to be a ln of 2 over 10 days to the minus 1, okay, and has some initial number of nucleons equal to n, or nuclei, not nucleons, excuse me, n naught. Then for bismuth, 210, half-life is 5 days. Lambda of 210 is ln of 2 over 5 days to the minus 1, and you have n naught number of nucleons, nuclei. I don't know why I keep saying nucleons, excuse me. Now, 10 days represent one half-life for actinium 225, right? So the activity for 225 after 10 days is going to be n naught over 2, okay, times ln of 2 over 10. So you're gonna have n naught ln of 2 over 20 for the activity, okay? But the n is gonna be days to minus 1. For the activity of 210 though, 10 days represent 2 half-lives. So we will have n naught over 4, because we start with n naught. In one half-life, we are left with n naught over 2, and in another half-life, we are left with n naught over 4. Okay, so we have n naught over 4, and then ln of 2 over 5, because to find the activity, you have to multiply by the lambda. I forgot to mention that. Okay, so this results in n naught ln of 2 over 20 days to the minus 1, just like for actinium. So that's actually true. I mean, we explained it using math. Okay, so I hope this is enough. So same activity after 10 days. Okay, so this was question 13. Let's move on to question 14. Okay, question 14. The diagram shows the spectra produced by two stars. Spectrum A is produced from the light from the sun, and spectrum B is produced from the light from a distant star. The dark lines are produced when light from the core of the star is absorbed by hydrogen atoms in the outer regions of the star. Light is then re-radiated, but in all directions, giving rise to the dark lines in the spectrum. A. Explain why the long wavelength lines are shifted by a greater amount than the short wavelength lines. And by the way, I mean, I'm gonna use red because it's red shifted. So you see that we can consider the sun as the laboratory. Okay, if that makes sense, because it's very close by. It's not red shifted, maybe a little bit, but compared to the spectrum from a very distant star, the sun kind of represents the lab. Okay, so this line shifts there, then this line shifts there. We have this shift, and then this shift, and then this shift. Okay, so you can kind of see that the longer the wavelength, the longer the shift. So why is that? So recall that delta lambda over lambda is equal to V over C, which is equal to Z. So delta lambda is actually equal to Z times lambda, okay? So with Z constant, right? Because it doesn't change for each line, correct? So with Z constant, delta lambda increases as lambda increases. So longer lambdas are more redshifted. Okay, B. I'm going to erase this and you will see why. Okay, B, one of the lines in the hydrogen spectrum occurs at a wavelength of 656 nanometers in the laboratory. Okay, so it's this line pretty much. Okay. Okay. Explain what conclusion can be made from the shift in wavelength of this line in spectrum B. Your answer should include a calculation. Okay, it's kind of weird, but let's pull up the ruler, which if you watched my previous videos, I don't really like using. I don't know. I studied theory. I'm a theoretical physicist, so I don't really like measuring things, I guess. So I don't know. This is a very cheap excuse, but whatever. So, okay, so you see that between 600 and 700 nanometers, there are how many centimeters? 1, 2, 3, let's say 4, and a little bit more. Okay, so each centimeter is about 25 nanometers, maybe a little bit more. So let's go see where this line is. So it's, let me think. So definitely 1 centimeter, and then a little bit more than 1 centimeter. So let's call it 40. Okay, so let's say that okay, let's remove the ruler now. So I'm trying to say that this line is about 740 nanometers. If you measure it and you disagree and you find 750 or 730, I think that's not a terrible thing. I mean, it still works. I mean, the physics is what matters, I guess. But let me know what the mark scheme says, because I don't really check them. I like to solve the problems myself. But yeah, okay. So let's say that lambda is lambda reference. So lambda reference is what we see on the sun. So 656 nanometers, and then the lambda we are interested is 740 nanometers. Okay, so delta lambda over lambda is equal to 84 over 656, and 84 is what you get. I guess, okay, I was sloppy. 740 minus 656 over 656. This yields 0.13, and we know that this is equal to Z. So V over C is 0.13. So V is 3.84 times 10 to the 7 meters per second. So the spectrum of the spectrum from star B, okay, is redshifted because the star is moving with 3.84 times 10 to the 7 meters per second away from us. So away from us because it's redshifted. Okay, so this is a beautiful thing, I think. I mean, this whole spectra business became available to scientists just 100 years ago. I mean, okay, it sounds like a long time ago, but the big scheme of things, it was yesterday, right? So when quantum mechanics was discovered, in case you don't know, they figured out actually quantum mechanics was kind of invented to explain the spectra that they observed from cathode rays, I believe. So, but anyway, at some point they figured out quantum mechanics around 1925, something like that. So 100 years ago, okay? And using this spectra, they were able to actually discover helium. So helium was discovered in the sun. That's why it's called helium, like the god Helios, the Greek god Helios. Okay, so it was discovered in the sun by its spectrum because they were measuring a spectrum of something that was not known on Earth. Okay, so they figured it's a different element, and then they discovered it via chemistry on Earth. Okay, and also they discovered this thing with the planets, sorry, with the stars receding and stuff like that. It's kind of fascinating if you think about it. So let's move on to question 15. Aluminium, okay, question 15, is one of the most widely recycled metals. Aluminium, cans are heated from room temperature until all the aluminium has melted. The molten aluminium is then used to make new cans. This process uses only 5% of the energy needed to extract aluminium from raw materials. On a website, it is claimed that recycling one aluminum can of mass 14 grams saves enough energy to listen to music on a mobile phone continuously for 7 days. Assess the validity of this claim. Okay, another trivia because it just hit me. Aluminium used to be really difficult to extract until they discovered some method involving high currents or something like that. I'm not up to date with this. I mean, it's something I read a long time ago. But anyway, back in the time of Benjamin Franklin, when aluminum was discovered, or a little bit later, it was considered the most valuable metal on Earth. So they made an aluminum statue of one of the founding fathers in the US, I think maybe Franklin, I'm not sure. And they made it from aluminum because it was so valuable at the time, because it was really difficult to extract. So, anyway, and I think the reason is that it's contained within other ore that's difficult to separate, something like that. So, but you should ask a geologist. So, let's assess the validity of this claim. So, first of all, we need energy to raise T for aluminium from room temperature. They give us the room temperature as 293 K to 660 K. Okay, so this energy is going to be C m delta theta. So the specific heat capacity for aluminium is 902, and then joules per kilogram per Kelvin times the mass, 14 times 10 to the negative 3 kilograms, because you have to convert, times delta theta, which is 660 minus 393, and this is kelvins. Okay, so this is equal to 4634.5 joules. Then we need energy to melt 14 grams of aluminium. So this energy is going to be the mass of aluminium times the latent heat. So 14 times 10 to the negative 3, and this is kilograms, times the latent heat of aluminium, which is 396,000, because kilojoules, okay, joules per kilogram. So the energy is to melt the aluminium is 5,544 joules. Okay, so okay, so the total energy is equal to 4,634.5 plus 5,544. So we find 10,178.5 joules. Okay, we will need a clean page now. Okay, now for the mobile phone, and I will come back to this actually a little bit later. So let's keep that for now. So the power of the mobile phone, okay, is going to be equal to the current times the voltage. So 120 times 10 to the negative 3 times 3.7 is the power of the mobile phone. So 0.444 watts. So in a week, the energy in a week is going to be 0.444 watts, which are joules per second. Okay, times 7 days, times 24 hours in a day, times 60 minutes in an hour, times 60 seconds. 60 minutes in an hour, and then 60 seconds in a day, in a minute, sorry. So 268,531.2 joules. But we are not done yet. We have to perform one more calculation. They tell us that the energy for recycling is 5% of the energy needed for extraction. Okay, so the energy needed for extraction, which is what we save, is actually equal to the recycling energy, which is 10,178.5 over 0.05. So this is not the energy we save. There is one more calculation we need. So 203,570 joules will be the energy needed to extract 14 grams of aluminum. Okay, so energy to extract 14 grams of aluminum. Okay, so how much do we save? So energy saved is actually 203,570 minus what we actually spend to melt it, which is 10,178.5. So the energy saved is 193,391.5 joules, which is less than 268,531.2 joules. So the claim is false. So claim is false, but not horribly false. I mean, it's kind of close. Actually, let's see how many cans we will need. So if we divide 268,531.2, which is the mobile energy we need for a week, over the energy we save by melting one can, which is 193,391.5, we find 1.4 cans. Okay, so the claim is kind of close. Okay. Anyway, this was question 15. Let's move on to question 16. Okay, question 16. In an investigation of the photoelectric effect, electromagnetic radiation of frequency F was directed onto a metal plate. The maximum kinetic energy E of the photoelectrons emitted from the metal plate was determined. The procedure was repeated for a range of frequencies. The graph shows how energy depended upon frequency. Determine a value for the Planck constant H in joules times seconds. Okay, first of all, let's write down the equation first. So H times the frequency of the photon goes into the work function plus the maximum kinetic energy of the electrons. Okay, so key max is equal to H times the frequency minus the work function. So the gradient, which is equal to the change in kinetic energy over the change in frequency, will be equal to the, okay, so the gradient is equal to H, right? So now let's draw a line of best fit. Let's use red. Okay, so let's connect all these points together. No, that's not a good line. I don't like it. Let's delete it. So let's do this instead. Okay, yes, this passes through all the points pretty much, right? Okay, so we can choose any 2 points on this graph to calculate the delta key. So I'm gonna choose this one and this one. Okay, so that's the distance we need for, okay, so this is delta key E and this is delta F. And I did this earlier, so I'm going to quote the values. So 1.85 minus 1.25 times 1.6 times 10 to the negative 19, because this is in EVs. And then in the denominator, we have 99 minus 85 times 10 to the 13. So, and the value is going to be joules times seconds, because hertz in the denominator convert into seconds in the numerator, and then the numerator is in joules. So we are good. So the result is 6.86 times 10 to the negative 34 joules per second. Maybe I didn't do a good job. Be more meticulous when you work with these values. So maybe you will find something closer to 6.63, which is the accepted value. But that's not bad. So, okay. Let's move on to part B. The table gives data for different metal surfaces. So cesium has a work function of 2 EVs, calcium 2.9 EVs, etc. Deduce which metal was being used in the investigation. Okay, so this is a tricky thing that the Edexcel does. Okay, the y-intercept, I mean, according to this equation, the y-intercept should be the work function, right? So if we extend this line there, this is going to be the work function. No, that's wrong, because frequency starts from 50, not from 0. Okay, so it's tricky. So it's better to use actually that point over there. So let's use this point, which is the x-intercept. Okay, so so at that value, at the x-intercept, the kinetic energy is 0. Okay, so we can do x-intercept means kinetic energy is 0. Therefore, the work function is h times f naught. Okay, so we're going to use the h we calculated, so 6.86 times 10 to the negative 34. And then the value there is about 56. I was checking it earlier. So this is 60, 58, 56, 54, 52 actually, maybe. So let's do 52 times 10 to the 13. So I will need to calculate this. Actually, let's use 56 that I had earlier, and you can work it out on your own. So you need the x-intercept, okay? So in my notes, I have 3.84 times 10 to the negative 19 joules, which is, if you convert to EVs, by dividing. So if you divide by 1.6 times 10 to the minus 19 joules per EV, you get 2.4 electron volts. So cesium is the closest. So cesium. Okay, but my values are exaggerated, because maybe that should be a 52 and maybe this should be a 6.7 or something like that. So try to play with the graph until you find a better result than me. And you should, because you guys are younger and sharper. Okay. All right, this was question 16. Let's move on to question 17. So for those of you who watch my videos, I recently messed up, and I was really sad about it. I messed up a ray diagram. I mean, it happens to the best of us, guys. But I provided an explanation in my in the community postings that YouTube allows us to have, so you can find the answer there. But anyway, this is a different problem. Let's start. A simple astronomical refracting telescope consists of two converging lenses. Light from a star is brought to a focus by the objective lens and then viewed through an eyepiece lens as shown. Question A, part 1. In the arrangements shown, the final image is formed at infinity. Explain why the separation of the objective and eyepiece lenses is equal to the sum of their focal lengths. Okay, so I'm gonna do this in 2 steps, and maybe I will need a clean page. Let's start here and we'll see. So for the objective lens, okay, 1 over u plus 1 over v is 1 over f. Let's call it objective, and we have u tending to infinity, okay, because the star is practically at an infinite distance away, okay, because if the distance is, I don't know, 5 light years, that's 5 times however billions of kilometers away, so 1 over that is going to be 0, okay. So 1 over v is 1 over f naught, okay. So v is equal to f of the objective, and image, okay, image forms at the focal point, okay, of the objective lens, okay. And I will need that clean page to do the eyepiece lens. So for the eyepiece lens, we have the same equation, of course. 1 over u plus 1 over v is 1 over f of the eyepiece. I'm going to call it fe. So if the image forms at infinity, okay, this time, then we have 1 over, okay, of course, 1 over v is going to tend to 0. So we will have 1 over u equal to 1 over fe. So u, the object, is at the focal point of the eyepiece lenses. But the object for the eyepiece lens, so the object for the eyepiece lens is the image of the objective lens, okay. So with v equals to f of the objective, so the image for the objective is formed at the focal length of the objective lens, and and u equal to fe for the eyepiece length, okay, for the eyepiece length, not length, I don't know why I said length, then the two lenses must be fe plus fo away. And we can actually see this because, okay, so you have a light from a distant star at infinity, so the rays, excuse me, are parallel, so this is going to be fo, and at the same time this is going to be fe, okay. All right, part 2 of this question. State why the final image is inverted. So the objective lens, and by the way, you see, no, this is not what I want. Yeah, let me continue. So the objective lens inverts the intermediate image, this one, okay. The eyepiece lens, so the eyepiece lens then magnifies the already inverted image, okay, without flipping it again. And this is because the image forms in the same side, so the image is going to be at infinity, but somewhere there, okay. So I mean in the same side as the object for the eyepiece lens. Okay. All right, let's move on. B, glass lenses used for optical instruments often have an anti-reflective coating. The coating is a thin layer of a transparent substance with refractive index, and C, light is reflected from the coating surface and from the lens surface as shown. The reflected light interferes destructively. Okay, when a single layer coating is used, the coating thickness is chosen to eliminate reflections for green light, which is in the middle of the visible spectrum. Question I, calculate the minimum thickness D of the coating required for the reflection of green light to be eliminated. So, we need a pretty much, let's use green since they mentioned green. Okay, so we need these rays to destructively interfere with rays that travel inside the coating and then they reflect back. Okay, so these lenses, these rays, I don't know what's wrong with me, I'm tired. So these rays have to interfere destructively. Okay, so the path difference, which is this, so the path difference, again, let me explain it again because maybe it's not clear. So let's say that you have rays that reflect off the coating, okay, and then rays that go through the coating and reflect on the lens and come back, okay. So these rays will travel 2D, okay, so 2D is the path difference between this ray and this ray, okay. So 2D needs to be equal to lambda over 2, okay. So that's the key. But then the velocity of the rays inside the coating is actually c over n of the coating, okay. And this is actually equal to lambda times f. So lambda, in fact, is c over f times n of the coating. So if we plug everything in, we have d is equal to 1 over 4 times c over f times n of coating. And if we plug in numbers, we have 3 times 10 to the 8 over 4 times the frequency for green light, 6 times 10 to the 14 hertz times 1.38. So everything works out to be 9.06 times 10 to the minus 8 meters, which interestingly, it's 90.6 nanometers. So this is a very, very small coating, okay? I hope this makes sense. This is, I was surprised to see a question like this at the A levels because these are the kind of questions that I got at the university when I first took optics. I think in my second semester or something like that. So this is a difficult question. So you have to be proud of yourselves, guys, for going through problems like this. So let's move on to part 2. State why white light reflected from coated lenses is seen as purple. So we can say that coating eliminates green, which is in the middle of spectrum, right? Okay, but red and blue go through, blend, and appear as purple. Okay, I mean, if you blend these two colors. So again, this is a difficult question because it requires for you to think creatively about something that you wouldn't expect at the A levels, but they ask this kind of questions to, I guess, rule out who the best students are and stuff like that. So yeah, it's good to remember your colors and how they mix, guys. I guess apparently. So okay, this was question 17. Let's move on to question 18. Okay, question 18. The harp or arp, I don't know how it's pronounced, let me know. The arp is a musical instrument with many strings as shown. And being Greek, whenever I see this instrument, I immediately think of Apollo and his lyra, because in Greek it's called the lyra, but it's an arp. It's the same thing. Actually, both arp and lyra are Greek words. So anyway, so there is a temple of Apollo kind of close to my home. So yeah, I mean, I live in ancient ruins, guys, which is kind of symbolic because I mean, the island is kind of a little is a little bit backwards sometimes. But yeah, anyway, but I do like the god part, okay? The gods part. So all the strings are under tension. The strings on one type of arp are made from nylon of density 1,700 1,700 kilometers per cubic meters. I'm sorry, guys, it's been a long day. One string has a diameter of 1.14 millimeters. Show that the mass per unit length mu of the string is about 1.1 times 10 to the negative 3 kilograms per meter. Okay, so let's start with the density, which is mass times volume. And these strings are kind of like cylindrical, right? So something like that. So they have, oops, so something like that. They have a surface area pi d squared over 4 and a length, okay? And the volume is going to be pi d squared over 4 times L, the volume of a cylinder, right, guys? So m over pi d squared times length over 4. But then immediately we see that mass over length is mu, right? So let me keep using red. So mu is rho times pi d squared over 4. Okay, and I always try to reach a final algebraic expression before I plug in numbers, because if you start plugging in numbers, you will get lost. I get lost. Okay, so it works for me. So rho is 1,070, and then kilograms over cubic meters, and then pi, and then d squared. Whenever you square quantities, it's good to use parentheses. So d is 1.14 times 10 to the negative 3 squared, and then meters squared. Let me transfer this a little bit further up. So there, okay. And the whole thing over 4. Okay. So meters squared cancel, and meters cubed cancel. So we find 1.09 times 10 to the negative 3 kilograms per meter, which is 1.1 times 10 to the negative 3 kilograms per meter. Okay, so this was question A. Let's move on to part 2 of question A. When the middle of the string is plugged, a node of frequency 440 Hz is produced. Calculate the tension in the string, and they give us the length of the string. Okay, so plugged in the middle means that we are in the basic frequency or node. So it looks like this. In other words, lambda, let me think, lambda is 2, so lambda over 2 is actually L, okay? Because where half a wavelength is equal to the length of the string, okay? And I drew it like this. It means that it vibrates like that, okay? So the speed of this wave is going to be equal to the square root of the tension over mu, the mu we just calculated, mass per unit length. But the velocity of a wave is lambda times its frequency, and this is equal to t over mu. Then if we square, we have, okay, this is the part where I will plug in lambda is actually 2L, so 2LF is equal to squared is equal to t over mu, so t is mu times 4L squared F squared. And if we plug in values, we find 109 times 10 to the negative 3 kilograms per meter times 4 times 0.41 squared meters squared times 440 squared. And then we have seconds in squared in the denominator. Okay. So we have kilograms times meters per second squared, which are newtons. So 141.9 newtons. So we can round to about 142 newtons. How do I know that kilograms times meters per second squared are newtons? Because I don't know why it did that. So F is MA. So newtons are equal to kilograms times meters per second squared. Okay, moving on. B, the graph shows how the Young modulus E of the nylon varies with temperature. So you see that it decreases when the ARP is played. The temperature of the string increases. Explain how this temperature change would affect the frequency of the note produced when the string is plugged. So the Young modulus decreases as the temperature increases. Okay, lower Young's modulus means the string's material is less stiff. So under the same fixed length, right? The tension decreases. But the velocity of the wave is equal to the square root of the tension over mu, and F, the frequency, is equal to V over lambda. Okay, and lambda is fixed because it's equal to 2 times the length, right? So a lower T means lower V and lower F. Okay, so we will have a lower frequency pretty much. All right, I think this is it, yeah, for question 18. Let's move on to the next question. Question 19, a fine beam tube is used for investigating properties of electrons. An electron beam is produced inside a spherical glass bulb. The bulb contains neon gas at a very low pressure. Question A, the neon gas is at a pressure of 1.25 pascals and a temperature of 25 degrees Celsius. Calculate the number n of neon atoms inside the bulb. The bulb diameter is 16 centimeters. Okay, ideal gas law. So PV is nKT. So N is PV over KT. Okay, so it's the volume of a sphere. So let's plug in numbers. 1.25, and this is Pascal, so newtons per meter squared. Then the volume is 4/3 pi times the radius squared. So the diameter is 16 centimeters, so the radius is 0.08 meters, so 0.08 cubed, and this is meters cubed. And then we have to divide by 1.38 times 10 to the negative 23 joules per Kelvin, right? And then the temperature is 273 plus 25 because we need kelvins. So kelvins cancel, meter squared cancel, and then newtons times meter is joules, and joules cancel. So we get a pure number as we should, because this is number of atoms, which is a number. So 6.52 times 10 to the 17 atoms. Do they mention the material? the element, excuse me. They don't, do they? No, but it doesn't matter. Neon gas, yeah, okay. So 6.52 times 10 to the 17 neon atoms. So part B. Long writing problem because of the asterisk. My favorite, not my favorite, but let's do it. Interactions between electrons and the neon atoms in the tube make the beam visible. Part of the spectrum of visible light produced by these interactions is shown. Explain the process that results in the emission of the spectrum. Your answer should include reference to energy levels in atoms. So let's start by saying that electrons in the beam, okay, collide with neon atoms. Okay, and transfer energy to them. And transfer energy to them. Okay, this makes electrons within the neon atoms, okay, move up to higher energy levels. In other words, the atoms get excited, right? The electrons in neon have discrete energy levels. So only specific energy jumps are allowed. Okay, when an excited atom, so when an excited, atom drops back down to a lower energy level, a photon is emitted. Okay, we'll need extra space. The energy of each emitted photon equals the difference between two energy levels. Okay, so delta E is h times the frequency, because only a limited number of energy levels exist. Only specific frequencies are emitted, producing a unique spectrum, like the one we see, the one we observe. Okay, let me be more scientific in my language. So this was question 19, a long problem, okay, just because of the writing part. So let's move on to the next problem. So question 20 involves a silly flamingo that we see there. We have flamingos in Cyprus. There is a salt lake, actually two salt lakes on the island. And these guys frequent the salt lakes in the winter, I believe. I should know this, but yeah, in the winter, because in the summer, the lake evaporates and only salt remains. So they visit from Africa, I believe. It's a migratory bird that flies from somewhere in Africa to Cyprus during the winter. I don't know, something like that. Or maybe, does it fly from the north? Okay, look it up. So, a garden ornament consists of a metal flamingo suspended from a spring as shown. The spring is hung from a support using the hook. The mass of the flamingo is 65 grams. When the flamingo is suspended vertically, the spring extends by 8.5 centimeters. Okay, so this part allows us to calculate K. But let's keep reading. The flamingo is pulled downwards by a small extra displacement and then released. The flamingo undergoes simple harmonic motion vertically. The instructions state that the flamingo will oscillate with a frequency of 2.5 Hz. Deduce whether this statement is correct. Okay, let's calculate K for the spring. So M times G is Kx. So K is going to be M times G over X. So this is 6.5, or no, 65, right? Forgive me, guys. It's been a long day. So 65 times 10 to the negative 3 times 9.81 over X. We have to convert to meters, so 0.085. So K is 7.5 newtons per meter. And now the period is 2 pi times the square root of mass over K. So F is the inverse of that. F is 1 over T, so 1 over 2 pi times the square root of K over M. So 1 over 2 pi, the square root of 7.5 over 0.065 yields 1.721 Hertz. So not 2.5 Hertz. So claim is false. Okay. B. After being set into vertical oscillation, the flamingo comes to rest after a short time. Explain why the flamingo comes to rest. So there is damping. So there is damping due to air resistance or internal friction in the spring. So there is damping acting on the flamingo. Okay. These forces remove energy from the system, from the oscillation. Okay. And the amplitude decreases to 0. Okay. C. In a slight breeze, the flamingo swings from side to side and behaves as a simple pendulum. Show that the period of oscillation of the flamingo is about 2.2 seconds, and they give us the pendulum length. So in this scenario, we have to think about the flamingo oscillating like a pendulum, okay? So the period is going to be 2 pi times the square root of L over G. So 2 pi times the square root of 1.25 over 9.81, which yields 2.2 seconds. Okay. Finally, part 2. The amplitude of oscillation of the flamingo pendulum is 7.5 centimeters. Calculate the maximum velocity of the flamingo pendulum. So Vmax is omega times the amplitude, so 2 pi over the period times the amplitude, so 2 pi over 2.2 times 0.075, which is 0.21 meters per second. This was question 20. Let's move on to question 21, which is the final one. Okay, so this is a really long paper. So the viewer who suggested that this is hard was actually right. I mean, it's not really hard as it's long, so maybe you will get confused and tired while going over this paper. But anyway, let's move on. 21. 100 years ago, a method to determine the age of certain rocks was developed. An unstable isotope of rubidium, okay, is present in some rocks. When they form, over time, the rubidium decays to a stable isotope of strontium. A. Rubidium decays to strontium via Vida minus decay. Complete the nuclear equation representing this decay. Okay, so the Vida particle has a 0 mass number and a -1 proton number, charge number. Why am I blanking right now? I'm tired, guys. So its Z is -1. Okay, and the proton number in strontium has to be 38 then, because 38 -1 has to be 37. Okay, and the mass number is 87 because we just then add 87 and 0 just give us 87. So that's the equation. Okay, part B. A sample of moon rock from the Apollo 11 mission was analyzed to determine the age of the rock. When the sample was analyzed, the number of rubidium atoms was Nr and the number of strontium atoms was Ns. As strontium atoms have all been produced from the decay of rubidium, the original number of rubidium atoms in the sample was Nr plus Ns. From the analysis of the sample, it was determined that Ns over Nr is 0.0532. Deduce whether the ratio is consistent with the Earth and the Moon forming at the same time. Okay, this is quite involved, but in essence, what they tell us is that the number of rubidium atoms remaining is equal to the initial number of rubidium atoms, N naught, e to the minus lambda t. But this is equal, okay, let's save space. So Nr is equal to Ns plus Nr e to the minus lambda t, because they tell us that the original number of rubidium atoms was equal to Nr plus Ns. So we are using that, okay? And then, let me erase this. We can bring e to the lambda t to the left-hand side. Okay, if this is not clear, ask me in the comment section and I will provide answers. But e to the minus lambda t becomes 1. It's like dividing these with e to the lambda t and then moving these to the left-hand side. Okay, so let me erase that so we can continue. So e to the lambda t is equal to Nr plus Ns over Nr, right? And if we take the log, the natural log, we have lambda t is equal to the ln of Nr plus Ns over Nr. Okay, so let's move to a clean page. So t is 1 over lambda, and then the ln of Nr plus Ns over Nr. Okay, so time is equal to t1 half over ln of 2, because lambda is ln of 2 over t1 half, right? Times the ln of 1 plus Ns over Nr. Okay, because I divided Nr with Nr, which makes 1 plus Ns plus Nr. And now we can plug in numbers. So 4.88 times 10 to the 10 years, right? Over ln of 2 times ln of 1.0532. And the final result is 3.65 times 10 to the 9 years, which is less than 4.5 times 10 to the 9 years, which is the age of the Earth. So the rock is younger. Okay, shocker. So the moon is younger than the Earth, so it wasn't formed. It's not part of the Earth. I mean, there is a theory that there was this planet called Theia, I think, that collided with the young Earth, and then the young Earth and Theia merged, and then the moon was separated from this violent collision. And anyway, so the Earth and the moon are the same thing, split apart or something like that. But then there are crazy theories. I mean, there are lots of crackpots out there dealing with this kind of questions. So I've heard theories ranging from aliens, hollow moon, artificial moon. I mean, there are people who support that it's an artificial construction. I've heard that in the dark side of the moon there is a war going on between the Nazis and Soviets. You know, you can read all sorts of things, and I love crackpot theories, guys. I mean, conspiracy theories are just the best. And there is this other guy. Um, I think his name is Tsoukalos. He used to make this show called what was the name? Ancient Aliens, and he supports that the pyramids and all that were constructed by aliens. So anyway, all these things are funny. Okay, so anyway, let's move on. Okay, part C. Give a reason why the half-life of the rubidium isotope is hard to determine. So it's really long. So it's really long. So the activity of any sample is hard to monitor. And remember that the half-life, what is it? It's 49 billion years, guys. So I'm gonna write it there. T1 half is 49 times 10 to the 9 years. And recall that the universe is 15 billion years old. So you have to wait for 3 times the age of the universe for this thing to, I mean, for half of this nuclei to decay. So it's a very slow process. So it's easy, it's prone to mistakes, to errors. Okay, not mistakes, errors. I have to use proper scientific English when I teach. I'm sorry. So part D. Recent investigations suggest that the half-life of the rubidium isotope may be larger than the traditionally accepted value. Explain how this will affect the ages obtained by this dating method. Okay, so lambda is a ln of 2 over t1 half. Okay, so if t1 half increases, then lambda decreases. Okay, so from t equals to ln of n naught over n times lambda to the minus 1, okay, a smaller lambda gives a larger t, okay. So the rocks might be older. Okay, so the conspiracy theorists might lose again in that case. And by the way, this equation, I went a little bit fast over it, but it's the usual n is n naught e to the minus lambda t. So that's a lambda, okay. So e to the lambda t is n naught over n. So lambda t is a ln of n naught over n. So t is 1 over lambda ln of n naught over n. Okay. So this was paper 2, Advanced Physics 2 from 2022. Indeed, a hard paper in the sense that it was long, too many questions, too many things to think about, and too many things to mess up. So yeah, I hope this is useful. Please subscribe, guys. 90% of people who watches these videos are not subscribed, so I kind of need the subscriptions and the watch hours because I want this channel to be monetized at some point. So maybe I can make a living out of it. I don't know, but yeah, it's a stretch at this point. Anyway, guys, thank you for watching. Thanks for the nice comments you write in my videos sometimes. It's really encouraging. It helps me keep going. Please recommend this channel to people who might find it useful. Leave likes and subscribe and leave comments. I mean, it helps with these videos popping up in YouTube searches. So anyway, wish me luck, guys. I mean, I keep going and I don't know, see where this goes. So see you in the next video. Bye.